We're still dealing with two-dimensional flows, and now our focus will be on bifurcations. In this lecture, the focus will be on saddle node bifurcations. We start with a very brief introduction to bifurcations. In two-dimensional flows, fixed points can be created or destroyed or destabilized as parameters in the system are varied. In fact, the same is also true for closed orbits. So we offer a very simple definition of a bifurcation. We say that a bifurcation has occurred if the phase portrait changes its topological structure as a model parameter is varied. For example, this could include changes in the number or stability of fixed points or closed orbits as a parameter is varied. So here are some examples of types of bifurcations. We have a saddle node, we can have a transcritical, we can have a pitchfork, and you can have a Hoff. So we look at a saddle node bifurcation in some more detail. Recall that the saddle node bifurcation is the basic mechanism for the creation and the destruction of fixed points. The prototypical example in two dimensions is x dot is equal to mu minus x square, y dot is equal to minus y, where mu is a parameter. So now let's consider the phase portrait as mu varies, and we consider the cases mu greater than 0, equal to 0, and less than 0. We first start by looking at the case mu is greater than 0. Now here there are two fixed points, x star y star is equal to the square root of mu 0, and x star y star is equal to minus the square root of mu 0. As we note, we have a stable node and a saddle. Now let's look at mu is equal to 0. As mu decreases, the saddle and the node approach each other and then collide when mu is equal to 0. And with mu less than 0, the fixed points actually disappear when mu is less than 0. So the fixed points disappear and we have this ghost region which appears in the phase portrait. So the ghost is a bottleneck region that sucks trajectories in and delays them before they actually leave the region. The time spent in the bottleneck generically increases as mu minus mu critical to the power minus a half, where mu critical is the value at which the saddle node bifurcation actually occurs. The justification comes from the same reasons as the analysis of one-dimensional flows. Now consider the following figure. Let's consider a two-dimensional system. X dot is equal to f of xy, y dot is equal to g of xy, that depends on a parameter mu. As shown in the figure, we assume that for some values of mu, the null lines intersect. Note that each intersection corresponds to a fixed point, since x dot is equal to 0 and y dot is equal to 0 together. In order to observe how the fixed points move as mu changes, we should be observing the intersections. Now suppose that the null lines pull away from each other as mu varies, essentially becoming tangent at mu is equal to mu critical. Then the fixed points approach each other and collide when mu is equal to mu critical, and after the null lines pull apart, there are no intersections and the fixed points actually disappear. The essential point is that locally all saddle node bifurcations have this character. So let's consider an example. So we consider a simple model for a genetic control system. We start with some basic background. The activity of a certain gene is assumed to be directly induced by two copies of the protein for which it codes. So essentially, the gene is stimulated by its own product, potentially leading to an autocatalytic feedback process. Note, autocatalysis is the catalysis of a reaction by one of the products of the reaction, and catalysis is the increase in the rate of a reaction due to the participation of an additional substance called a catalyst. So the equations in dimensionless form are x dot is equal to minus ax plus y, and y dot is equal to x squared divided by 1 plus x squared minus by, where x and y are proportional to the concentrations of the protein, and the messenger RNA from which it is translated respectively. A and B are parameters that govern the rate of degradation of X and Y. So here are a list of questions. Show that the system has 3 fixed points when A is less than A critical, where A critical is to be determined. Show that 2 of these fixed points coalesce in a saddle node bifurcation when A is equal to A critical, and sketch the phase portrait for A less than A critical and give a biological interpretation. Now let's look at the solution in some detail. The underlying equations are x dot is equal to minus ax plus y, and y dot is equal to x squared divided by 1 plus x squared minus by, where a and b greater than 0 are system parameters. The null lines are given by the line y is equal to ax and the curve y is equal to x squared divided by b times 1 plus x squared. Now let's plot y versus x, and that's y is equal to x squared divided by b times 1 plus x squared, and that's the line y is equal to ax. Note that this is for a small value of a. We plot another line y is equal to ax, and this is for a large value of a. For small a, we have 3 intersections. As a increases, the line will intersect the curve tangentially. For larger values of a, the origin will be the only fixed point. And to find a critical, we need to compute the fixed point directly. Now note that the null lines will intersect when ax is equal to x squared divided by b times 1 plus x squared. So one solution is x star is equal to 0, and so y star is equal to 0. And the other intersections satisfy. AB times 1 plus x squared is equal to x, which actually has 2 solutions. X star is equal to 1 plus minus 1 minus 4 a square b square square root divided by 2ab. If 1 minus 4 a square b square is greater than 0, i.e. 2ab is less than 1, so the critical curve is 2ab is equal to 1, and so a critical is equal to half times b. Note that the fixed point x star is equal to 1 at the bifurcation. Now let's plot the null lines to learn about the phase portrait, especially when a is less than a critical. So now let's plot y versus x. That's the line y is equal to ax, and now we plot the sigmoid shaped curve, which is y is equal to x squared divided by b times 1 plus x squared. The vector field is vertical on the line y is equal to ax and is horizontal on the sigmoid curve. The other arrows were sketched by noting the signs of x dot and y dot. It seems that the middle point is a saddle and the other 2 points are sinks. So we highlight the sink and that's a saddle. We now turn to the classification of the fixed points. The Jacobian matrix at xy is A is equal to minus A, 1, 2x divided by 1 plus x square whole square minus b. A has trace minus a plus b, which is less than 0. So all the fixed points are either sinks or saddles, depending on the value of the determinant delta. At 0, 0, delta is AB, which is greater than 0. So the origin is always a stable fixed point. In fact, it is always a stable node, since tau square minus 4 delta is equal to a minus b whole square greater than 0, except in the case a is equal to b. At the other two fixed points, delta is equal to ab minus 2x star divided by 1 plus x star square whole square is equal to ab times x star square minus 1 divided by 1 plus x star square. So delta is less than 0 for the fixed point x star less than 1 and greater than 0. So this is a saddle point. The fixed point with x star greater than 1 is always a stable node, since delta is less than AB, and therefore tau square minus 4 delta is greater than a minus b whole square, which is greater than 0. Let's plot the phase portrait. So a plot of y versus x. That's the sink, that's the saddle, that's the sink. Note that the unstable manifold of the saddle is trapped in the channel between the two null clients. Also note that the stable manifold separates the plane into two regions, each of which is a basin of attraction for a sink. Now it's always a good practice to try and relate the results back to the original real world problem. So the biological interpretation is that the system can act like a biochemical switch, but only if the mRNA and the protein degrade slowly enough, i.e. the decay rates should satisfy AB less than a half. In this case, there are two stable states. One at the origin, so the gene is silent and there is no protein to actually turn it on. And one where X and Y are large, so the gene is active and sustained by a high level of protein.
In this lecture, we discussed the transcritical and the pitchfork bifurcations in two-dimensional flows. Now, these are bifurcations that have counterparts in one-dimensional flows as well, and we note that the pitchfork comes in two variants, a supercritical and a subcritical. Now, if you want to construct the normal forms for these bifurcations in two dimensions, all you do is look at the normal forms for these bifurcations in one dimension and add the equation y dot is equal to minus y, and we'll have the normal form in two-dimensional flows for these bifurcations. So to that end, there isn't much of a conceptual leap of faith in going from one-dimensional flows to two-dimensional flows, except to mention that it eminently could be possible that the algebra actually gets much more involved in typical two-dimensional examples.